Live. All right. So what we're going to do today is kind of talk about how we get to the two equations that we are going to be using for this chapter. We are starting a new chapter. This is chapter 3. It is all about accelerated motion. Okay. So last chapter we did talk about how we can calculate average acceleration. But what I want to do is give you two equations that we can use for almost every type of accelerated motion. Okay? Everybody good? All right. So we are going to do some moving around of variables and some math because I want to give you an idea of where these equations come from because I don't like to just spring equations on you without any explanation. Okay? So we are going to start with our average acceleration equation, and we are going to get a standard equation for our velocity. We are going to change our variables up a little bit and just change our notation just so we have less subscripts overall so that if you're writing it out fast, it's a lot easier to write. Make sense? Okay. So what we are looking for is an equation for final velocity. Okay? So we're going to start from this, solve for velocity, which we've already done. That was one of our 3 equation forms for this. So we should get delta V equals A delta T. Good? You vaguely remember this? We also talked about how delta V is going to be our final velocity minus our initial velocity. What we really want to know most of the time is going to be our final velocity. So we are going to expand this. So we get V final minus V initial is our A delta T. And now we want to solve for our final velocity. So we're going to add this to both sides. Good? Okay. Just a side note, as we get into some longer equations that have more plus signs, I do always try to be very careful to put a hook on the bottom of my T so you can tell them apart from my plus signs. Good? So that's a T, that's a plus sign. Now, this equation is one that you could have used last chapter, right? So this one's not anything crazy, not anything out of the ordinary. This one's pretty straightforward. It is pretty much what we used last chapter. Now, this is where we're going to introduce a little bit of a new way of writing out our variables. It's not hard. I just want you to know what each thing's going to mean. Okay? So we're going to simplify this a little bit. Most of the time, we are going to be solving for our final velocity. Okay? So instead of leaving this little f here, we're just going to call it v. And just know that the velocity we are solving for is our final velocity. Good? Yeah? So this is still final velocity. We've just dropped the f. All right, our acceleration, we're not going to change. It's already as simple as we can make it pretty much. For our delta t, once we start using this equation, we're just going to kind of understand that it is the amount of time that we were accelerating for. Okay? And so we're actually going to drop the delta and just say, hey, this is our time interval. Good? Just so that we don't have to write the delta every time. We've got the no delta there. And then we're going to change the way we write our initial velocity. This notation indicates that this is going to be our velocity at t equals 0. Okay, we've dropped the t equals, and that's why we have a 0 here. If you ever watch like a YouTube video of a professor talking about this, a lot of times they will call it v naught, and this kind of comes from the English pronunciation of 0, and it just means that it's your initial velocity. Any questions? No? Okay. Just to make sure everybody's good. So final velocity, acceleration, time accelerating for, and then our initial velocity. Everybody good? Yeah? Okay. All right, let's do just a real quick example with this. Let's see. All right. So we have a person that has an acceleration of 1 meter per second squared for 3 seconds, and they start with an initial velocity of 2 meters per second. We want to know how fast they're going after these 3 seconds. Okay? So we're going to use this equation to find our final velocity, because that's what we want to know. We want to know how fast they're going. So we're going to say our velocity equals, what's our acceleration? 1 meter per second squared. What's our time? 3 seconds. And our initial velocity? It's 2. Okay? All right, when we multiply these together, one of our seconds is going to cancel out, so we do get units of meters per second. So we get 3 meters per second plus 2 meters per second gives us 5 meters per second. So like I said, these are not hard. This type of problem is really not any different than what we did last chapter. Good? Any questions? Yeah. All right. Things to watch out for. Make sure you look at your units just to kind of double check that what you are putting in place fits in that spot. So if it's acceleration, you should have meters per second squared. If it's time, it should be measured in seconds. If it's velocity, it's meters per second. Good? Everybody good? All right. Now, we're going to go on to the slightly longer equation. It's really not any harder. It's just long. Now, to really understand where this one comes from, we would probably need to go into calculus. Since none of you probably have done calculus before, we're going to go about it kind of a roundabout way and talk about kind of how we can experimentally add things into equations. Good? All right. So for this, we are going to start with one of our old equations. So you can see that some of it is very similar. So we're going to start with the velocity equation this time. And what we want to solve for is final position, because we want an equation that will tell us where we are if we have an acceleration. Okay? Because we don't have one of those yet. We didn't talk about that last chapter. So we're going to use the form that says delta x equals v delta t. Okay? And we want to find our final velocity, so we will expand this again. And we want to solve for final, like I said. So we end up with okay. So we haven't done anything weird yet. Nothing out of the ordinary. We just have the equation we would have had last chapter. Any questions? All right. So we want to move this to the same sort of notation that we had before. Okay? So we're going to drop the f on the x. So we just have x as our final position. Our velocity, because we are actually going to start adding acceleration in here, we do need to specify that this is our initial velocity here. So we're going to use the same notation we did before. Put the little 0 down here. So this is v naught, or our initial velocity. We are going to drop the delta t. Okay, so we're going to drop the delta. Just know that that is the period of time you are accelerating for. Okay? So we've got v naught t, And then we're going to do the same thing with this. We're going to drop the I and put that little 0 there. Good? Okay. Now, to kind of talk about how we can add acceleration into this equation, I kind of want to look at the structure of it first. Okay? So, if we didn't have velocity, right, so if our velocity was 0, this equation would tell us that our final position is equal to our initial position, right? Yeah? That makes sense. That's what we would hope it would tell us, right? Because if we're not moving, we should stay in the same spot. Then, to add in velocity, we added on a term, okay? And this term tells us how far we go if we're going this speed for this amount of time, right? Okay? Because it gives us a distance, we know that we have units of meters here, right? Yeah? Okay. So the next term we want to add on needs to tell us how far we go if we accelerate for a certain amount of time. Okay? So we know that we need to have something to do with an acceleration and something to do with time in that term. Okay? And when I say term, a term denotes like something that's multiplied together, but is then added in an equation. Okay, so this is a term, this is a term, okay, and we're adding another set of multiplied things onto it. Okay, everybody good? Okay. So this is going to be our general form. We know we have to have acceleration in there. We know we have to have time in there. Okay. We also know we have to have units of meters because you cannot add meters per second to meters. It wouldn't make sense, right? You can't add a speed to a distance. They're not the same thing. Good? So if we look at our units for meters per second, or acceleration, they're meters per second squared. And time is going to be seconds. So if we have it like this, is it going to cancel our seconds out completely? No. What would we have to do to get our seconds to cancel out? Any ideas? Yeah.
Square them.
Okay, so if we square time, we also have to square our units. So now we get seconds squared here. Now it does cancel out, and we're left with meters. Okay? So our term that we're going to add on is going to have this form. Okay, so our variables are going to be like this. Now, one thing that you do have to check in science is that this reflects what we see in real life. Okay? Because there might be like a number out front, or a constant, as we would call it. Okay? And so a scientist trying to figure out what this equation would look like would take this and say, okay, I know I need an equation of this form because otherwise I can't add this term in. It's not going to give me the right units and stuff like that. But I can put a number out front. So I'm going to go do experiments and see what the experiments give me. Okay? Then a lot of times they're going to plot their data like we did on some sort of a graph. And they would then generally use a line of best fit to see if there is a number out front. We have computers now that will do this for us. And if we actually did this, we would find that we do need a number out front. Okay? This number is 1/2. Okay? So this 1/2 we find because we need it to fit real life. And so we kind of find this from experimentation. Cool? So we now have the full term that we can add into this equation to give us our proper numbers for real life. So our final equation is this. Okay? Now, I know this is probably the longest equation that you've ever used in class. I will tell you right now, most of the time, a lot of things will be 0 and so you won't have to use all of the terms. Okay? The reason why we have it written like this is because this is our general case. This works for pretty much every situation you would ever want to use it for. Okay? Even if you have no acceleration, this will still work. Good? Okay. So I do want to write out what all of these are, just so that you have this in your notes. That's our final position. Okay? So, just to make sure everybody can see everything, this is your final position. This is your acceleration. This and this are going to be the same number. They're both the same variable. You would put the same number in there. After you put the number in is when you square this. Okay? Already got that? Okay. This is our initial velocity. This is our initial position. Okay? So let's do the same example we did before and see where he would end up. So we know how fast he'd be going. But let's see where he'd end up. So we had a guy who was accelerating with an acceleration of 1 meter per second squared for, did I say 3 seconds or 2 seconds?
3 seconds.
3 seconds. And then he had an initial velocity of 2 meters per second. Good? Okay. So on this equation, because it's so long and has so many variables, sometimes people actually like to make a list of their variables. So I want to show you how to do that. So if you make a list of all of our different variables, you should have 5 in this equation because t is repeated twice. Okay? In this case, I asked you how far he would go for this motion. Okay? That means that we need to find our final position. Okay? For a situation like this, I like to put a question mark next to the variable I'm looking for, just so that I know I don't need to go searching through my problem to find it. Good? Okay. What's our acceleration?
1 meter per second squared.
1 meter per second squared. Our time?
3 seconds.
3 seconds. Our initial velocity?
2 meters per second.
2 meters per second. If I do not specify, we'll assume that we start at 0. Okay, so our initial position is 0. Everybody good? Okay. Now we go put our numbers into our equation. So we leave x as x, because that's what we're looking for. Don't forget your 1/2. It is important. You can't forget to divide something in half. It'll give you a wrong answer if you do. So don't forget that. All right, so we are going to go through this kind of step by step, okay? One thing that I want to mention is the order of operations in your terms, because it's all multiplied, doesn't matter a whole lot. The one exception is you do have to square the time. Okay, so the time is the only thing that is squared. Good? Okay, so we're just going to start here and say, what's 1/2 times 1?
1/2.
1/2. Our units haven't changed here because 1/2 didn't have units. What's 3 squared?
No.
9. Don't forget that you also have to square your units. Okay? What's 2 times 3?
6.
Here our units have changed actually. The seconds should cancel out, so we're left with meters. What happens if we add 0 meters?
Nothing.
Nothing. So 6 plus 0 gives us 6. Okay? What's 1/2 of 9?
4.5.
4.5. Now we do have to take care of our units. Our seconds are going to cancel out. We get meters plus 6 meters gives us
10.5.
10.5. Is this equation as scary as it looks?
No.
Okay? If you take it slow, and if you're having trouble, if you write out your variables like this, it shouldn't be hard to use. Okay? Any questions? No? All right. This is actually a fairly difficult problem for what I would give you. Okay? I just wanted to show you how things will go in different places, show you that you do put the same time in for both, because that's something that people get confused on. Most of the time for problems in this class, your initial velocity is probably going to be 0. Okay? And if your initial velocity is 0, this whole term becomes 0. Okay? Because if this is 0, no matter what you multiply it by, it's going to be 0, right? Okay? So when you have those zeros in there, it'll take entire terms out and make your life a lot easier. Good? Any questions? No? All right, how much time do we have left? Let's do one more example. Okay? Let's do an example where there are a lot more zeros, like I said. All right. So let's say we have a person starting a race. Okay? They are going to start at a position of 0 and an initial velocity of 0 meters per second. Okay, so they're at the starting line. They're going to start this race. Let's say that we know they have an acceleration of, how fast do you want their acceleration to be?
40.
That's an impressive acceleration. Okay. How long are they accelerating for?
2 minutes.
2 minutes. Okay.
It's the dude that ran the marathon in 2 hours. It's pretty cool.
Just to put this in perspective, a good, really, really, really quick conversion from miles per hour to meters per second is take this and multiply it by 2.
Yes,
Okay.
right.
So this person has an acceleration of 80 miles per hour per hour.
For how long? For 2 minutes?
Yes.
It
It actually is going to be a little bit different because the second conversion is going to be, yeah. So this guy's going to be going really fast.
You're running like Mach 1 by the end of the day.
I anticipate that he will probably be going faster than the speed of sound, yes. All right, anyways. All right. Let's see how far he travels in 2 minutes. Because that's also going to be very
A
confusing.
lot of meters.
Yes, it is going to be a lot of meters.
Because that's what I want, okay?
All right. So we want to know how far he travels. So which variable are we looking for?
Final,
Okay. So we're looking for x. What's our acceleration? 40 meters per second. meters per second squared, just to make sure that's clear. How long? Our time?
120 seconds.
120 seconds. Initial velocity? 0. And position? 0. Okay? All right, so I'm going to write this out real fast. All right, so as I said before, when we have zeros, it makes a big difference in this equation, okay? So here, right, what's 0 times 120? 0, right? So we now have 0 here and 0 here. What's anything plus 0?
The same thing.
It's just whatever you started out with. So we can now completely ignore those two terms.
Nice.
Okay? So all we're left with is this part here. So we get 1/2 of 40 gives us 20 meters per second squared. What's 120 squared?
1,440.
Nice.
It should have a lot more zeros.
Oh wait, no, one more zero at the end.
Yeah.
14,000.
Keep going fast.
Yeah. Can somebody check this on the calculator? 'Cause I'm not sure. There might be
Wouldn't
another.
it be 12 times 12 with 2 zeros at the end? Like 12 squared.
I guess so, yeah. That should be right. So, what's 20 times 14,400? It is a lot.
Yes, it's a lot.
288
A
with 3
big
zeros at the end.
number.
Okay. Just for the fun of it, let's see how many miles this is. Just for the fun of it.
In 2 minutes. I'm not on steroids, you're on steroids.
So this is about 18 miles in 2 minutes.
That's not a lot.
It's 17.8 miles. A 5K is like 3.2 miles.
How fast you think?
28, I think.
How far do you
A
go?
5-minute mile is pretty fast. And you just ran
Oh, 5.
18 miles in 2 minutes.
Which is a 9 mile in 1 minute.
Yes. So yes, this is fast. Have a good day, guys.
No, I can't.